Okay, here we are again to talk about circles. Today we're going to be talking about tangents of circles, which is a little bit different than when we think about the word tangent from trigonometry. But actually, before we get into that, we're going to do a little bit of practice, some problem solving here with this warm-up. So the warm-up says that circles B, C, and D all intersect at point E. So you can see that the big circle has E as a point on it, this medium circle has E as a point on it, and then the small circle has E as a point on it. If BG is equal to 10 units long, then find each measurement. So BG right here is 10, and it's representing a radius of this big circle B. And you might remember that all radii are congruent, so every single one of these is going to be 10, which means BE is also 10 units long. Now, BE not only is a radius of the super big circle, but it's also the diameter of our medium-sized circle. So if the diameter of our medium-sized circle is 10, then its radius is 5. So BC will be 5, which also means CE, which is a radius of that medium-sized circle, is 5. Now, not only is CE a radius of our medium circle, it's the diameter of the small circle. So we'll use that information to find CD. So take a second, pause the video, see if you can figure out how big is BC, how big is CD. So BC is the other radius. I've actually already marked it in my picture, so that's 5. So the two radii of circle C, that medium circle, are both 5. Now CD is the radius of the small circle, but the radius of the small circle is really just the half of the radius of the big circle. So half of that 5 would be 2.5. All right, the last thing it asks us to do is find BD. Now we're going to do a little segment addition. You might remember that from first semester. So BC is 5 and CD is 2.5, so BD would be 7.5. All right, so now that we've kind of got ourselves warmed up on circles, let's talk about something new, and that's a tangent line to a circle. So a tangent line to a circle is a line that crosses the circle at exactly one point, and that point is called the point of tangency. All right, so what does that mean? Well, if the line is tangent, it's only going to cross the circle in one spot. So if we had a circle and we crossed it here, do you see that that crosses in 2 spots? So that's not quite a line of tangency. If we draw a circle and we draw our line here, well, that line doesn't even touch. So a line of tangency, a tangent line, is going to be a point that touches, or a line that touches in only one point. So it's only going to touch the edge of the circle. It won't go through the circle. Okay, so we're going to do a little bit of discovery here. It says draw a tangent line anywhere on the following circle. So I've got a little bit of drawing up here. So I'm going to put my point of tangency down here. And then I don't have a ruler with me, so I'm just going to use a piece of paper here. And I'm going to use that to draw the best line that I can, only touching in that one spot. So that's my tangent line. Now we're going to connect the point of tangency to the center of our circle. And that connection there is a radius, right? Because it's going from the center of the circle to the edge. All right, now we're going to measure the angle created by the tangent line and the radius. So we're going to measure this angle right here. So I don't have a protractor either. I left all that good stuff at school, but I am going to use this piece of paper here. So this corner right here I know is 90 degrees, and if I put that right in the corner, do you see that it lines up exactly on the edges there? Which means this is 90 degrees. So these two line segments, the radius and the line of tangency, are perpendicular, which means they form a 90-degree angle. All right, so our first theorem then comes from this kind of discovery activity. So if a line is tangent to a circle, then it is perpendicular. So then it is perpendicular to the line drawn to the point of tangency. Now that's just a really fancy way to say a radius and a tangent line. Oh, I can't spell. Tangent line form a right angle or are perpendicular. Now that's going to come in really handy because we know that we can do stuff with right triangles. So not only do we have Pythagorean theorem with right triangles, we could do 45, 45, 90 triangles, 30, 60, 90 triangles. We can do trigonometry. So having that right angle there is going to be super duper important and super duper helpful. All right, so let's do some stuff with this information. So if we look at our first picture here, it says find the length of AB. What we know right now is we have circle C. C is our center. CB is a radius. CD is a radius. D is our point of tangency. I'm sorry, B is our point of tangency because it's where the line's only touching one spot of our circle. Now, if CB and CD are both tangent lines, then, both radii, then they are both congruent. So this is also 5. And the radius and the tangent line are perpendicular, which is where our right triangle comes in. So this is a leg, and this is a leg, and this is my hypotenuse. So we've got to find AB, which I'm going to call x. So we can use the Pythagorean theorem. So 5 squared plus x squared equals, now we have to use this whole thing, so 8 plus 5, which is 13. So 25 plus x squared equals 169. X squared equals, we're going to subtract 25 from both sides, and x equals 12. So AB is equal to 12 units. All right, so in this next one, we're going to use the same ideas, but we're going to have to do a little thinking out of the box here. So again, we have circle D, because it's named by its center. E is our point of tangency. DE and DF are both radii, which means if DF is 9, DE is 9. And we're going to find FG, so I'm going to call that X. Okay, radius and tangent line are always perpendicular, creating our right triangle. So we can use the Pythagorean theorem again. So we've got 9 squared plus 12 squared equals, now here's where we have to be careful. Our hypotenuse is both of these pieces together. So if this is 9 and this is X, then the whole thing would be X plus 9. All right, so 9 squared, 12 squared, X plus 9 squared. All right, so add these guys together, 225. Now from here, I could multiply this out, but since this whole thing is being squared, we can actually just square root the whole thing to get our squared and our square root to cancel out. So the square root of 225 is 15. And then if the squared and the square root cancel out, we're just left with x plus 9. So then to find x, we're just going to subtract 9. So x equals 6, which means x is representing FG, so FG equals 6 units. So anytime you have a radius and a tangent line, they will always be perpendicular, which means we're going to be able to use the Pythagorean theorem. All right, next problem, or this is actually going to lead us into our next theorem. So it's more properties of tangents. So draw a point anywhere outside of circle O. So circle O is over here. We can draw that point anywhere we want. I'm going to put it just right here. Create as many tangent lines as you are able that connects this point that you just drew to circle O. So remember, your tangent line can only touch in one spot. So I'm going to go from this, looks like I can draw one right here. So there's my point of tangency. If I turn it a little bit, now it's crossing my circle. So I don't want it to cross my circle. So I'm going to keep going till it only touches my circle in one spot if I can. Oh, looks like I might have one right here-ish. All right. All right, so how many lines were we able to make? Only 2. Now, I don't have a ruler, so I'm gonna do the best I can here, makeshift. So I'm measuring this tangent, or this little segment here, this portion of the tangent line, just using my note card. Do you see that those segments are the same length? So from this point outside my circle to my point of tangency, these segments are the same length. So the tangent segments are the same length. So there are 2 tangent lines that can be drawn from an external point. So this right here is my external point to a circle. So these are my 2 tangent lines from my external point to my circle. The segments from the external point to the point of tangency, so this segment here and the segment here, will be congruent. So how is that helpful? Well, let's look at circle. Just going to draw a triangle off this. Okay, so you can see that in this one I have a circle, I have 3 external points, and that means I have 3 points of tangency also. So this theorem tells me that this segment here will be congruent to that segment there, because external point, point of tangency, same external point, point of tangency. It also tells me that this segment here and this segment here will be congruent. External point, point of tangency. So this to here will be congruent, and then finally this little guy here and this little guy here will be congruent because external point to the point of tangency. All right, so if we use this kind of as a helper or a clue, let's look at this last problem. Find AD and AC. So we want to find AD, which is this length here, and we want to find AC, which is just this length here. So what do we notice about our picture? So we have circle E. ED is a radius, and it's 8. EB is a radius, so it's going to be 8. And CE is a radius, so it's going to be 8. According to this theorem, AB, external point to the point of tangency, and AD should be congruent, which means AD is also 20. So we've already found AD. So all we need to do now is find AC. So I'm going to call that X. Well, from our first theorem, the radius and the tangent line are perpendicular. So we already know we have a right triangle. So we can set this problem up like the 2 we did above. So 8 is a leg and 20 is a leg. And then our hypotenuse isn't just 8, and it's not just X, it's this whole segment. So we're going to call that X plus 8. Don't forget to square it. All right, so now we just got to do some math here. So 64, 400. So 464 equals X plus 8 squared. So we're going to square root both sides. So the square root of 464 It's a crazy decimal, so it's about 21.5. So 21.5 equals, now the square root and the square root will have canceled each other out. So now we're just going to subtract 8 from both sides. So I actually shouldn't put an equal sign because it's not equal, it's approximately equal, right? Because we rounded that decimal. So we're going to call that x is approximately 13.5 centimeters. So don't forget those units. All right, that's all there is to today's notes. So give the homework a try and reach out if you have any questions. I'm always happy to help. Otherwise, have a fantastic day.